We are still going at 4.3. What's next? We know how to find increasing and decreasing. We know how to find local maximums and local minimums using the first derivative test. Oh, but there's more. We'll be able to figure out where our function is what we call concave up or concave down. Concave up and concave down talks about a curvature. So there's a graph of a concave up to the best of my ability. So if you're concave up, you're basically you're curving upwards, right? Going from left to right. Even though it's coming down at first, right? It's like it's fighting it, right? It's curving up, it's curving up, it's curving up, it's curving upwards, and there you go. What would be true about derivatives when your graph is curving up like this, when it's concave up? So it turns out it's the second derivative that's positive for a concave up section of your graph. Why would that be? So you notice the first derivative doesn't tell us much, right? So at first it's decreasing, right? Tangent lines are going down. Then at some point there's a minimum and the tangent line that is horizontal. Then it starts going up, tangent line is positive. But if we think about how the motion happens, we can see why the second derivative would always be positive throughout. Notice that even though it starts off with negative tangent lines, those tangent lines are getting less negative as we move across this shape. At some point, right, they're very negative here, they're getting less negative. At some point they hit 0, and then they start to become positive. And they are a little bit positive, and then more positive, and then more positive. Think of that like acceleration. It's becoming more and more positive, right? Your velocity is increasing. Hence, the second derivative is positive. What about if your function is concave down? It's got this downward sort of shape, this downward curvature. So again, from left to right, maybe it's going upwards, but it's pulling downwards. At some point it peaks and then it keeps pulling downwards like so. Well, as you can imagine, that's when the second derivative is negative. Similar argument, right? If you thought about the first derivative, the slopes of the tangent lines, they're really positive, but they're becoming less positive. Then at one point they become 0, and then they start to go negative and then more negative. So it's like almost like you're decelerating, or you're even like going in reverse in your car. You're like speeding up in reverse. You're going you're backwards faster and faster. You have a negative acceleration. Okay, well, think like, hey, so if I was to plug an x value into the second derivative, I could tell if the graph was concave up or concave down there. This is going to lead to our concavity test. Another test to test where it seems like we got a lot of tests at this point. It turns out the concavity test is identical to the increasing and decreasing test. It just uses the second derivative instead of the first derivative. So let's talk about the steps. Find the x values where the second derivative is 0 or where the second derivative does not exist. That's the equivalent of critical numbers, but with the second derivative. Okay, we don't have a name for it, but where is the second derivative equal to 0? Where does the second derivative not? I mean, that's it. That's critical numbers for the second derivative. We're going to mark those on a domain line, right? Similar. And then we're going to test a value from each interval, but we're going to test those values into, of course, the second derivative now to see if those are either increasing or if that interval we're testing is, to see if that interval is concave up or to see if that interval is concave down. All right. And again, I'll note that this is identical to the increasing decreasing test, except we're using f double prime x. There's one other thing we have to define, the inflection point. An inflection point is a point where f of x changes concavity, where it switches, say, from concave up to concave down or vice versa. Let me give you a picture what that would look like. So in that picture of f of x, right, at first it's concave down, and then it passes through that purple point, and then it switches and starts to become concave up. So right at that one moment, it makes the change. The inflection point is the equivalent of the local max or min, right? A local max or min is where it changes from increasing, increasing, decreasing, you know, whichever way it is. An inflection point is where it changes concavity. Okay, with that in mind, let's check out this example. Find intervals where f of x is concave up and concave down, then find any inflection points. And we're gonna use f of x equals x to the fourth e to the negative x. Okay. Let's just say find intervals of concavity, then find any inflection points. Okay. And our function f of x equals x to the fourth e to the negative x. Right. Well, only one option here. We have to use product rule, which we like anyway. 4x cubed e to the negative x plus x to the fourth times, and now chain rule on that, e to the negative x times -1. Let me clean that up just a little bit. 4x cubed e to the negative x minus x to the fourth e to the negative x. Okay. Because we're looking for concavity, we need a second derivative. So here we go again. Notice now we have two product rules. So let's carefully do each of these. The first product rule, 12x squared e to the negative x plus 4x cubed times e to the negative x times -1. Okay, looks good. Minus, now be careful here, because we're subtracting and then doing a product rule, we need to make sure that minus sign goes to both parts of our product rule. So we'll say minus and then product rule here. This is actually the same product rule we did from the beginning, so it's going to be this again. But okay, right, 4x cubed e to the negative x plus x to the fourth times e to the negative x times -1. All that in those large parentheses. Let's clean that up just a bit. Don't know if there'll be any like terms, maybe. Oh, maybe these, maybe those in the middle. Okay, let's see here. One step at a time. 12x squared e to the negative x. This will be minus 4x cubed e to the negative x minus another 4x cubed e to the negative x, and then minus is plus x to the fourth e to the negative x. And yeah, we see that these terms here in the middle are going to combine. Okay, let's go ahead and simplify all of this. Minus 8x cubed e to the negative x plus x to the fourth e to the negative x. Looking good. Now that we have our second derivative, we need to figure out where this will equal 0. This sounds really bad, but you did it all carefully and you simplified. it actually isn't quite as bad as it seems. Okay, again, the key is factoring. What do these have in common? They all have an e to the negative x. They also all have x squared. So I'm going to take x squared e to the negative x, leaving me with 12 minus 8x plus x squared. That I'm going to rearrange the terms, make it look a little bit neater. X squared minus 8x plus 12 equals 0. That's something I'm more comfortable factoring again. X minus 6, x minus 2 would give me the positive 12 and the negative 8. Looks good. Okay, we got it factored. From this, I can see, hey, the x squared will give me a solution of x equals 0. I'm going to skip this one for the moment. Here we've got x equals 6 comes out as a solution and x equals 2. What about the e to the negative x? So it turns out, if you were to try to solve that like a factor, setting it equal to 0, right? There wouldn't be any solutions. There is no number that you can put in the exponent of e and produce 0, right? Even if you plugged in 0, e to the 0 equals 1. And then any other number, you know, they would actually all give you a positive result there. So there's no solution to this, which just means we've got 3, they're not critical numbers, but they're the equivalents, right? At 0, 6, and 2. Okay. Also, don't forget, even if it's only in your mind, in your head, any times where our second derivative is d and e. No, not here either. We're not dividing by x anywhere. We're good. Even though it has the e, it's not just a polynomial. Still, no cusps or anything like that. Okay, so far so good. We got our 3 numbers at 0, 6, and 2. What's next? Let's think about the domain of f of x equals x to the 4th e to the negative x. Again, this is the entire number line. So we can mark now our 3 numbers. Okay, at 0, 2, and at 6. That will do it. Let me copy over that second derivative again. 12x squared e to the negative x minus 8x cubed e to the negative x plus x to the 4th e to the negative x. Even if it's easier, you know, you say, hey, I could do that factoring again, right? X squared e to the negative x, 12 minus 8x plus x squared, right? And I could plug it into this if that was a little bit faster for me. Okay, now, oh, we've got 4 intervals. Let's begin. How about -1 into the second derivative at double prime -1? So if I put that in, let's see, to the whole thing, what would happen here? Well, -1 squared, that's nice. What would happen here? That'd be a 1, that'd be a +8, so that'd be 21. And then plugging it in here, -1 would be just e to the 1st, 21e. Again, the number itself, not important. Is it positive or negative? So that's positive, which means it's concave up. So I might do that like U shape for the concave up. But how about the next one? Well, I'm going to pick +1 now. Okay, I'll let you guys kind of verify this, but if I put in +1, that would get me 5e to the -1. Now here's the thing, this is still positive. E to the -1 means I'm taking 5 divided by e, but that's a positive divided by a positive. it's still concave up there. Interesting. Okay, the next one, how about 3? Well, I'll let you guys check. I got negative 27 e to the negative 3. Now that's negative because the negative in front. So we're concave down. And finally, f double prime, I'll use 7. I got 245 e to the negative 7. That's back to being positive. So positive concave up. So I've got it, concave up. Let's see, here, here, and here. Notice we got the 2 back to back. At 0 itself, it is not concave up. At 0 itself, the second derivative equals 0. So we cannot include the 0. We have to say it's from negative infinity to 0 union 0 to 2 union 6 to infinity. We have to break it up on either side of 0. Okay, how about concave down? And it's just at the one little spot between 2 and 6. So there it is, concave down. Hey, we got intervals of concavity. Now, what about inflection points? Okay, inflection points are where the concavity changes. That happens twice, at 2 and at 6. So there's an inflection point, there's an inflection point. 0 was not one. It was concave up, and then it kept being concave up. We'll see what the graph looks like in a minute. That's kind of an interesting case, right? Like, how does that work? But to answer the question right, inflection point here because it switched, and then it switched again at 6. So we need to get the y values. So we need to plug both 2 and 6 into the original function. What was that original function? It was actually a lot simpler than that second derivative. It was this. So we'll find f of 2. F of 2 is 16 e to the negative 2. And f of 6, 6 to the 4th, that's 1296 e to the negative 6. So we have, we'll just say inflection points. We don't have to distinguish like which type they are. There's only one type. There's one at 216 e to the negative 2, and there's one at 6 comma 1296 e to the negative 6. There we go. Hey, you know, we got to check out the graph in Desmos. Y equals x to the 4th e to the negative x. That kind of interesting shape there. Okay, let's think about the concavity first. Oh, you know what? We should plot the inflection points, and then we'll be able to see it. So we had an inflection point at 216 e to the negative 2. Notice we don't have to round anything. Don't round that number, that y value. If you don't need to, or if the instructions don't say, we'll just leave it with the e. We can put in here to Desmos just like that, and there it is. And the other one was at 6 comma 1296 e to the negative 6. Yeah, right there. All right. And yeah, we can see that. Looks like it's concave up at 0. What was happening at 0? So at the origin, it has a horizontal, well, it has a horizontal tangent line for sure. But even the second derivative, it like flattens out. Notice how much flatter this section is than, say, the top up here, right? So this section, you would think, well, oh, it's just concave up the whole way. It's actually not. It's concave up, And then for a moment, it's not curving up anymore because it just gets so flattened there at the origin. So for just one point, it's not curving up, but then it, like then the very next point after that, like infinitely close, it starts to curve back up again. So, but I think we can see, yeah, it really does flatten out quite a bit there compared to, say, this other peak here. It looks like it's at 4. Right? Okay, so it's concave up from negative infinity to 0, then skipping 0 from 0 to 2. Then it starts going concave down from 2 to 6. And then it's concave up again from 6 to infinity. Now you kind of look at that and you're like, this is really concave up? Yes, it is going down, and there is an asymptote, right? It's coming in down toward the x-axis. Yet it is curving upwards. So it never like turns the corner and starts going back up, but it is going downwards slower and slower. And so it has that like curling upwards sort of a characteristic there, attribute there, that it's curving away from the x-axis as it's going off to infinity. Even though it keeps getting closer to it, it's getting closer slower and slower. Pretty sweet. All right, let's stop this video here. Got one more topic in this section.